Section: Introduction. In this section, we discuss the significant advancements in video generation driven by the emergence of generative modeling techniques. We have observed that a lot of research has concentrated on adapting pre-trained text to image diffusion models for video generation. Recently, a groundbreaking model called Sora has made a substantial impact by scaling a spatial temporal transformer model. This model showcases impressive video generation quality, extending the length of generated videos from just a few seconds to an extraordinary full minute. This innovation is reshaping the landscape of generative AI and raises exciting possibilities for producing hours-long films. While most video generation methods utilize diffusion models, we note that these models are primarily designed for visual rendering and struggle with complex abstract reasoning compared to autoregressive models, which have proven effective in natural language processing. Additionally, diffusion models are not flexible enough to handle arbitrary video lengths. In contrast, autoregressive models excel at managing complex reasoning and predicting future events, which is crucial for creating a coherent world model. They also offer more flexibility in predicting varying lengths and benefit from established training and inference systems. Consequently, there have been efforts to apply autoregressive models to video generation. However, we recognize that autoregressive modeling is less efficient in terms of computation compared to diffusion models for visual rendering, requiring significantly more resources even for image generation. Recent findings indicate that we can consistently enhance video generation quality for short durations, from seconds to a minute, by increasing computational resources, following the scaling law. In our work, we choose to move beyond the challenge of short video generation and instead focus on developing a generative framework for long video generation that features complex narratives and intricate plot developments, which cannot be achieved simply by scaling existing methods. Our goal is to expand the possibilities of video generation beyond short content, allowing for the creation of videos with rich and engaging storylines. We introduce a hierarchical approach called MovieDreamer, which combines autoregressive modeling with diffusion-based rendering. This innovative method aims to achieve a balance between long-term coherence and short-term visual fidelity in storytelling. By leveraging the strengths of autoregressive models, we ensure consistency in key movie elements such as character identities, props, and cinematic styles, even during complex scene transitions. Our model predicts visual tokens for specific timeframes, which are then transformed into keyframes and dynamically rendered into video sequences using diffusion rendering. This process resembles traditional movie directing, where intricate plots are broken down into manageable scenes. Our approach maintains both the overall narrative and the detailed spatial temporal elements with high fidelity, enabling the automated production of visually cohesive and contextually rich movies. To represent the entire movie, we use sparse keyframes and employ a diffusion autoencoder to convert each keyframe into compact visual tokens. We train an autoregressive model to predict the sequence of these visual tokens, initializing it from a pre-trained large language model, specifically a 7 billion parameter llama model, to utilize its extensive world knowledge for better generalization. This model functions as a multimodal model, predicting visual tokens based on movie script conditioning rather than just generating text. During the autoregressive training, we focus on three key design considerations. First, we apply various model and input perturbation techniques to address the tendency to overfit, given the limited availability of high-quality movie training data. Second, we introduce a novel multimodal script that is hierarchically structured, containing rich descriptions of image styles and scene elements, along with detailed text descriptions of characters and their facial embeddings. This multimodal script promotes narrative continuity across different segments of the movie while allowing for flexible character control. Additionally, we randomly append a few reference frames before the visual tokens of the same episode, enabling the model to learn in context and produce high-quality personalized results, which is particularly beneficial for generating coherent continuations of movie episodes. We then decode the predicted visual tokens using an image diffusion decoder and render the images into video clips using an image-to-video diffusion model. Importantly, we enhance this process by fine-tuning an identity-preserving diffusion decoder, which effectively reduces errors in visual token prediction and improves identity preservation in the resulting video clips. Our work is complementary to current efforts aimed at enhancing short video generation quality through increased computational resources, and we can benefit from these advancements. We validate our approach through extensive experiments across various movie genres, demonstrating our ability to generate visually stunning and coherent long-form videos that surpass the state-of-the-art. In summary, our contributions include the introduction of MovieDreamer, a novel hierarchical framework that integrates autoregressive models with diffusion rendering to balance long-term narrative coherence with short-term visual fidelity. Our method significantly extends the duration of generated video content to thousands of keyframes, supports zero-shot and few-shot personalized generation scenarios, and accommodates variable lengths of keyframe predictions. We utilize a novel multimodal script that hierarchically structures rich scene descriptions and character identities, facilitating narrative continuity and enhancing character control and identity preservation. Our method showcases superior generation quality, with detailed visual continuity, high-fidelity visual details, and the ability to maintain character identities. Section Summary. In this section, we discuss the advancements in video generation driven by generative modeling techniques, particularly highlighting our novel framework, MovieDreamer, which combines autoregressive modeling with diffusion rendering to create long-form videos with coherent narratives and high visual fidelity. Our approach leverages a multimodal script for character control and narrative continuity, enabling the generation of visually stunning and contextually rich videos that extend beyond the limitations of short-duration content. Section: Related Work. In this section, we discuss related work in video generation, multimodal large language models, and visual story generation. First, we note that video generation has progressed significantly, primarily through diffusion and autoregression methods. The rise of stable diffusion has led to numerous studies aimed at enhancing video quality using various techniques. For longer videos, certain strategies have shown effectiveness. Although diffusion models are computationally intensive and can struggle with complex sequences, they remain popular. On the other hand, autoregressive methods are less frequently used but excel in specific applications, such as autonomous driving, by utilizing unified token spaces, even though they face challenges with continuity in intricate scenes. Our approach seeks to merge the advantages of both methods in a hierarchical and scalable way, providing better control and flexibility regardless of the video length. Next, we explore the advancements in multimodal large language models, MLLMs, which have led to the development of visual language models, VLMs. These models enable large language models to understand visual information, demonstrating their capability to generate images alongside text. Ongoing research has highlighted the strong abilities of MLLMs in interpreting video content, reinforcing the effectiveness of VLMs in tackling complex challenges. Building on this progress, we utilize VLMs to aid in generating very long video content. When it comes to visual story generation, the key challenge is maintaining consistency across the generated images. Similar to video generation, both diffusion and autoregression methods are commonly used here as well. In diffusion-based approaches, conditional generation is typically employed to ensure coherence, with some methods achieving promising results in preserving high-quality facial features and identities. Other methods rely on autoregressive principles, but these often produce average results and are difficult to scale. We recognize that story and video generation are closely related, sharing overlapping solutions. Our method uniquely combines these aspects, providing a cohesive approach. We propose a new framework for generating extended video sequences that harnesses the strengths of autoregressive models for maintaining long-term consistency and diffusion models for producing high-quality images. Our method uses multimodal scripts as conditions, predicts keyframe tokens in an autoregressive manner, and utilizes these frames as anchors to create full-length videos. We ensure flexibility by supporting both zero-shot generation and few-shot scenarios, where the generated results must adhere to a specified style. We pay special attention to preserving character identities throughout the design of the multimodal script, the autoregressive training, and the diffusion rendering. We illustrate our overall framework in a figure. To achieve concise yet accurate representations of images, we employ a diffusion autoencoder. Our encoder includes a pre-trained clip vision model and a transformer-based token compressor, which encodes an image into a reduced number of compressed tokens. The decoder then reconstructs the image using these tokens, adopting a pre-trained diffusion model to produce an image of specific dimensions. The latent image tokens are processed through the diffusion decoder using cross-attention. We train the compressor and decoder while keeping the clip vision model unchanged. The training loss for this diffusion autoencoder involves the input image and its corresponding noisy latent representation at a given time step, which is a combination of the original image and some noise. Our experiments show that just 2 tokens can effectively capture the main semantics of keyframes, supporting findings from previous research. For generating keyframe tokens in an autoregressive manner, we start with a pre-trained large language model, Llama 2-7B. Unlike traditional large language models, our model predicts the compressed vision tokens based on the input multimodal scripts and historical information. We define the model's function to predict these tokens from the previous history and the current script. Traditional large language models typically use cross-entropy loss for training, which works well for discrete outputs. However, since our model deals with continuous real-valued image tokens, cross-entropy is not suitable. Inspired by the Gaussian mixture model, GMM, we adopt a K-mixture GMM to effectively model the distribution of these real-valued tokens. This involves setting parameters for the GMM, which allows us to sample continuous tokens. We train the model by minimizing the negative log likelihood, considering the total number of frames and the number of compressed tokens per frame. Section Summary. In this section, we discuss our novel framework for generating extended video sequences by combining the strengths of autoregressive models for long-term consistency and diffusion models for high-quality rendering, utilizing multimodal scripts as conditions. We also detail our approach to keyframe tokenization using a diffusion autoencoder and the autoregressive generation of compressed vision tokens, which allows us to effectively model and generate video content while preserving character identity and coherence. Section: Anti-overfitting. In this section, we discuss our approach to combating overfitting in our generative model, which arises from the limited amount of high-quality video data we have collected. Although we managed to gather 50,000 long videos, resulting in 5 million keyframes for training, this volume is still relatively small. Consequently, we face significant overfitting challenges, where the model struggles to generalize effectively during testing. To tackle this issue, we implement several key strategies during training. First, we employ data augmentation techniques. By applying random horizontal flips and occasionally reversing the order of video frames, we significantly increase the diversity of our training data. Next, we focus on face embedding randomization to prevent identity leakage. We randomly select face embeddings of the same character from different frames, ensuring that the model does not simply memorize the training frames based on face embeddings alone. We also utilize aggressive dropout, applying a high dropout rate of 50%. This is essential for helping the model learn effectively from our limited training data. Additionally, we incorporate token masking, where we randomly mask input tokens with a probability of 0.15. This forces the model to infer missing information based on the context it has, which enhances its ability to generalize from incomplete data. We then develop a structured multimodal script format for autoregressive conditioning. This script integrates various elements, including characters, scene components, and narrative arcs. Since it is difficult to accurately represent a character's appearance using text alone, we combine textual descriptions with facial embeddings for a more comprehensive representation. We organize the script to clearly separate these elements, and for non-textual data like facial embeddings, we project them into a specific embedding space using a multi-layer perceptron. One challenge we face is that textual data often results in long sequences, which can consume too much token space and limit the model's ability to understand context. To address this, we treat text as a separate modality, breaking it down into identifiers and descriptions. Identifiers are brief statements that outline the script structure, while descriptions detail the attributes for generation. Each description is encoded into a single token, which allows us to extend the usable context during training by condensing entire sentences into single tokens. We use long clip as our text encoder for descriptions, which supports inputs of up to 248 tokens, enhancing our ability to manage detailed narratives. For personalized content generation, we propose a few-shot learning method that leverages in-context learning. During training, we randomly select 10 frames from an episode, encode them into visual tokens, and prepend these tokens to the episode's visual tokens. This approach not only encourages in-context learning, allowing the model to customize content based on reference frames, but also serves as a data augmentation technique to reduce overfitting. Our model is flexible, supporting both zero-shot and few-shot generation modes. In zero-shot mode, the model generates content based solely on a text prompt, while in few-shot mode, it uses a small set of user-provided reference images to better align the generated content with user preferences, without needing additional training. This ensures that users can efficiently create high-quality, customized visual content that matches their desired themes and styles. In our ID-preserving diffusion rendering approach, the main diffusion decoder effectively reconstructs target images but sometimes struggles with fine details, especially facial features, due to the loss of detail in compressed tokens. To improve this, we enhance the cross-attention module by integrating both descriptive text embeddings and face embeddings from the multimodal script. We also introduce a random masking strategy that obscures some input tokens, encouraging the decoder to better utilize available facial and textual cues to reconstruct images with greater fidelity, particularly in preserving identity-specific traits. This ID-preserving rendering compensates for identity loss during autoregressive modeling, leading to significantly improved identity perception quality. Finally, after obtaining keyframes from the movie, we can generate video clips based on these keyframes. A straightforward method is to use an existing image-to-video model, like stable video diffusion, which transforms input images into latent features for conditioning and interacts with the clip features of the input image through cross-attention. While this model can generate high-quality short videos, it struggles with longer clips. To create longer videos, we initially use the last frame of the previously generated video as the starting point for the next video. However, we found that this leads to a gradual decline in video quality over time due to error accumulation. To address this, we propose a simple yet effective solution. We always use the feature of the first frame as an anchor during video extension. This helps the model maintain awareness of the original image distribution. In practice, we utilize the clip feature of the original input image for cross-attention interaction when generating subsequent videos, rather than relying on the last frame of the previous video. Section Summary. In this section, we address the challenge of overfitting in our generative model due to limited training data by implementing strategies such as data augmentation, face embedding randomization, aggressive dropout, and token masking. We also develop a multimodal script format for autoregressive conditioning, utilize few-shot training for personalized content generation, enhance our diffusion rendering for better identity preservation, and propose a method to generate longer video clips by anchoring on the original input image features to maintain quality. Section: Implementation Details. In this section, we outline the implementation details of our approach. We utilize the UNet from the pre-trained SDXL as our diffusion decoder. The encoder is made up of a pre-trained clip image encoder, specifically the VIT-L model, along with a transformer-based compressor. We initialize our autoregressive model using a pre-trained Llama 7B checkpoint. All the multi-layer perceptrons, MLPs, that we use to align different types of inputs follow the architecture established in LLAVA. For more information, we refer readers to the appendix. Next, we discuss our dataset. To thoroughly assess the effectiveness of our method and make comparisons, we create a test dataset that includes 10 long movies, which are not part of our training set, resulting in 50,000 keyframes after we process the data. Each video goes through our data pre-processing pipeline, which accurately extracts and annotates keyframes. For every keyframe, we generate corresponding textual prompts and character face embeddings. We then evaluate the effectiveness of various methods using specific metrics. The clip score helps us measure the semantic alignment between the plot and the generated outputs. We assess quality through the aesthetic score, as Frechet image distance, FID, and inception score, IS. To evaluate consistency, we introduce metrics for both short-term, street, and long-term, LT, consistency. We measure short-term consistency by calculating the cosine similarity of clip between adjacent frames that feature the target character. Long-term consistency is assessed by checking if the target character appears in selected frames throughout the test set. Finally, we calculate the ratio of frames containing the target character to the total number of selected frames to measure how well we maintain long-term character consistency. When it comes to story generation, we note that many existing methods focus on fine-tuning with small datasets, which leads to poor generalization. Therefore, we only compare our method with those that show strong generalization capabilities, specifically story diffusion and story gen. As illustrated in our results, story diffusion struggles to maintain long-term consistency, as seen in the inconsistencies in the character's hair and the differences between keyframes. Similarly, story gen also fails to preserve consistency and produces unusual results. In contrast, our method successfully generates very long content while maintaining both short-term and long-term consistency across multiple characters. This is further supported by the quantitative results, where our method scores highly in both LT and ST consistency. Additionally, a higher clip score indicates that our generated results align well with the storyline, and better scores in IS, AS, and FID demonstrate that we produce high-quality images. We provide more qualitative results in the appendix. In terms of video results, we conduct a thorough comparison between our method and existing methods for generating long videos. For text-to-video methods, we use detailed descriptions from our test set as input. For image-to-video approaches, we utilize keyframes generated by our methods. Our results show that we significantly outperform previous open-source models in terms of quality, showcasing strong generalization capabilities. Most importantly, our method can generate videos that last for hours with minimal compromise in quality, achieving state-of-the-art results. More qualitative video results can be found in the appendix. We also analyze our approach, particularly focusing on anti-overfitting strategies. Large autoregressive models are powerful learners, which can lead to overfitting on the dataset. Our observations show that the generated content often reflects the input character too closely, producing similar visuals even with different text prompts. To combat this, we implement anti-overfitting strategies that reduce the direct link between character IDs and target frames, preventing simple memorization. This adjustment helps us produce diverse, high-quality results that align well with the text descriptions. Furthermore, we introduce multimodal movie scripts that incorporate face embeddings to enhance consistency. Our findings demonstrate that removing face embeddings reduces the model's ability to maintain character consistency. Face embeddings provide more detailed and precise information compared to text alone, allowing us to preserve both short-term and long-term consistency effectively. Regarding ID-preserving rendering, we note that our decoder already shows the capability to reconstruct the target image. However, for images not included in the training set, the reconstructed characters may appear slightly different due to the loss of fine facial features in the compressed tokens. After applying ID-preserving rendering, our decoder significantly improves its ability to maintain character identities. The experimental results clearly illustrate the effectiveness of this post-processing step. Lastly, we highlight our method's ability for few-shot personalized generation. Our approach acts as a powerful in-context learner, generating results that align with the style or characters from a few references provided by the user. The results showcase our model's capability to produce outputs that are consistent with the style and characters in a few-shot scenario.